In this video, we're going to be looking at topic 8A, Redox Chemistry, as part of the IAS Chemistry Unit 2 from Edexcel. So in this topic, we're going to be discussing oxidation numbers, how we can calculate these, how we can use the oxidation numbers to tell us the name of a formula, or how we can write the chemical formula. Also, how we use oxidation and reduction in terms of electron transfer, what we mean by oxidation and reduction agents, looking at disproportionation reactions, and being able to write ionic half equations or full ionic equations. So oxidation and reduction can be defined in two different ways. Oxidation can be the gain of oxygen or the loss of electrons, and reduction can be the loss of oxygens or the gain of electrons. Now, talking about it in terms of oxygen is sometimes used for inorganic substances, but we tend to use this more for organic substances. So we're going to be focusing on the loss or gain of electrons. And back in GCSE, you probably learned this mnemonic, which was oil rig. So oxidation is loss of electrons, reduction is gain. And when we have oxidation and reduction happening at the same time, we call this a redox reaction. So again, back in GCSE, you would have learned about oxidizing and reducing agents. So just to go back through what these are, an oxidizing agent is a substance that oxidizes something else. And it does that by removing one or more electrons. And because it removes electrons from another species, it itself is therefore reduced. So an oxidizing agent would be reduced in the reaction because it is causing something else to be oxidized. A reducing agent is therefore the opposite. A reducing agent is a species that reduces something else by donating one or more electrons, and therefore, by losing its electrons, it is therefore oxidized. So an oxidizing agent is reduced, and a reducing agent is oxidized itself, because the term reducing or oxidizing is talking about what it does to something else. So this is new for A level, and it is a disproportionation reaction. Now, disproportionation reaction is when a single species undergoes simultaneous oxidation and reduction. So in this reaction here, you can see that we have two copper atoms. And when copper oxide reacts with sulfuric acid, we can form copper sulfate and we can form copper. Now, what's actually happening here is one of these copper 1 ions that is present in copper oxide is being oxidized to copper 2 because it is losing an electron. We also make copper metal, or copper atom, and that involves gaining an electron, so this one is being reduced. So we are having the same element being oxidized and reduced in the same reaction. In order for this to happen, we of course need to have two of the atoms or ions that are present. Now let's look at the concept of an oxidation number. So when we've been using our other reduction and oxidation reactions, we've been looking at atoms and ions. And when we have atoms and ions, it's very easy to see what is being oxidized and what is being reduced. However, there are many compounds that can undergo redox reactions that are covalent, so they are not going to form ions, and that makes it a little bit more challenging to figure out what's being oxidized and what is being reduced. So to get around this, scientists came up with the concept of an oxidation number. And an oxidation number is either the charge that an ion has or the charge that it would have if the species was fully ionic. So we imagine that if our covalent compound was an ion, what charge would it form? And that number is then its oxidation number. So for example, if we take calcium oxide, which is ionic, the calcium is going to have a charge of 2+, so its oxidation number is 2+. Oxygen, in this case, has a charge of 2- as the oxide ion, so its oxidation number is 2-. Now, if we look at SO2, this being a covalent compound, we know that the oxide would form an 2 negative ion again. So this would have the oxidation number of 2 minus. So if sulfur in this example was fully ionic, it would have to balance out the 2 negative charge from the 2 ions of oxide. So that would cause it to have a charge of 4 plus, so its oxidation number is 4 plus. And we're going to look at some examples of how to do this in just a minute, but to make it a little bit easier, scientists have come up with a set of rules for oxidation numbers. So when you're calculating oxidation numbers, these are the rules that you should follow. If you have an uncombined element, the oxidation number is 0. The sum of the oxidation numbers of a neutral compound is also 0, and the sum of the oxidation numbers of an element and an ion is equal to the charge on the ion. So if it was SO4 2 minus, the oxidation numbers would need to add up to 2 minus. The more electronegative element is always given a negative oxidation number. That's meaning it is more likely to take the electrons and be reduced, therefore it is going to be negatively charged. The oxidation number of fluorine is always -1, and that is because it is the most electronegative atom in the periodic table. So of course it's always going to have a negative. The oxidation number of hydrogen is always +1, except when it is combined with a less electronegative element, usually a metal, in which case it becomes -1, because we've already said that the more electronegative element has to be the negative number. And oxygen is always 2-, except in a peroxide, where it is 1-, or if it is combined with fluorine, when it is 2+. Now, these exceptions that do exist, we need to know them, but they are quite rare when they come up in exam questions. They tend to stick to the most common rules that are in this list. So if we look at a few examples, we want to look at sodium and different compounds. Now, when you're using your metals, something that would be ionically charged, then we would simply use its position in the periodic table. So something that's in group 1 is going to have an oxidation number of 1 plus. If it's in group 2, it is going to have an oxidation number of 2 plus, and so on and so on. So that you can use the position on the periodic table to help you. So if we look at sodium chloride, the chloride is the more electronegative, so that's going to be our negative number. And chlorine is in group 7, so it's more likely to form a 1 negative ion, so its oxidation number is 1-. For sodium, it is going to be 1 plus because it is in group 1. Now if we look at NaClO, we can see that the sodium still stays the same. The sodium is going to be 1 plus. Oxygen, we know, is 2- because that's our rule. So here, the one that is changing is the chlorine. There are a number of elements that can have varying oxidation numbers, and it's typically the one that they ask you for. So if they give you these 3 questions in an exam, they would likely be saying, calculate the oxidation number of chlorine in each of these examples. So here, if the oxygen is -2 and the sodium is +1, this needs to all balance out to 0, so my chlorine in this case is +1 oxidation number. In the third example, the sodium remains +1 and my oxygen remains -2, but I need to take into account now that I have 3 of them. So -2 times 3 is -6. Again, all of this has to balance out to 0, so if I have -6 and +1, I need a +5 charge on my chlorine in order to balance out to be 0. So let's look at some more examples. So in this case, I've got sulfur and O3. The one that is underlined is the one that we want to work out the oxidation number for. So we know from our rules that oxygen is going to be -2, but if I have 3 of them, that gives me a total charge on the oxygen of -6. Notice that the charge on all of the oxygens is -6. That does not mean that the oxidation number of oxygen is -6. The oxidation number of oxygen is always -2. If I have -6 of my oxygen, I then need to balance that out to be 0, so my sulfur must be +6. If we look at MnO4, which is 2-, again, my oxygen has to be -2, and I have 4 of them, which gives me a charge of -8. I need to then work out what the manganese is going to be. So I need to get my overall charge to be -2. So if I have a -8 charge, I want to get up to -2. So to do that, I need to have 6 positives. So my manganese has an oxidation number of +6. If I look at ClO-, again, the oxygen is 2-. This time I only have 1 of them, so I just leave it as 2-. I want to get my overall charge to be 1-. So how do I do that? Well, my chlorine becomes 1+. And lastly, if I have ClO4, 1-, again, my oxygen is -2. I have 4 of them, so my charge on the oxygens is -8. I want to go from -8 up to -1, so I need to have 7+ as my oxidation number for the chlorine here. So I should have +6, +6, +1, and +7. And you can see that's the answers that I get. If you want to practice these, you can find lots of examples online, or please have a look at the A-level textbook. There are a number of examples in there, or if not, ask your teacher. So now we can use oxidation numbers to identify if a reaction is an oxidation or a reduction. So if we look at these half equations, we can see that we've got chlorine gas plus 2 electrons to give us 2 chloride ions. So the oxidation number here is changing from 0 to -1. For manganese, it is going from a +7 when it is in MnO4 to a +2. And the hydrogen and water is going from +1 to being an uncombined element, so it's going to 0. And each of these, the oxidation number has decreased, so reduction has taken place. So when your oxidation number decreases, you have a reduction reaction. And when your oxidation number increases, you get an oxidation reaction. Now, S block elements will either change from a 0 to a +1 or a +2, as we've seen with sodium or with calcium. P block elements are a bit tougher to predict because they can have varying oxidation numbers, but you will talk more about this in topic 8C when you're looking at the halides. So here we can use oxidation numbers to show if these are examples of redox reactions. This is a very typical exam question. They will give you an equation and they will ask you to show why this is an oxidation. And it's usually worth 3, maybe 4 marks, and it is up to you to identify the oxidation number of each element and then determine what has changed. So has it been oxidized or has it been reduced? So let's have a look at the first example. We have H2S plus Cl2 gives you 2HCl plus S. And you can see that we have worked out our oxidation numbers here. And for the sulfur, we have went from 2 minus to 0. So my oxidation number has increased. So therefore, the sulfur has been oxidized. And for my chlorine, I have went from 0 to 1 minus. So the oxidation number of chlorine has decreased. Therefore, it has been reduced. Since we have oxidation and reaction both taking place, this is classified as a redox reaction. If we look at part B, we have NaOH plus HCl to give us NaCl and H2O. The oxidation numbers here again have been determined, and what you can see when you compare each of them, that there is no change in oxidation number. Therefore, this is not a redox reaction. In actual fact, this is a neutralization reaction between an acid and an alkali, so it is not a redox. For example C, we've got NaOH reacting with chlorine to give us NaCl plus NaClO and water. Again, we check all the oxidation numbers for each element, and we can see that the chlorine has went from 0 to minus 1, but the other element of the other atom of chlorine has went from 0 to plus 1. So the number for chlorine has both increased and decreased. So yes, this is an example of a redox reaction, and we can classify even further by saying it's a disproportionation reaction, because of course the same element in a species has been both oxidized and reduced. Now we're going to move on to nomenclature using oxidation numbers. So because some elements can have different oxidation states, we have to specify in the name or in the systematic name of a compound what the oxidation number is. And we do this by using Roman numerals. So if we look at iron, for our first two examples, we have FeCl2 and FeCl3. So the iron can have an oxidation number of +2 or +3, and you will find out more about why that can have oxidation numbers in year 13. So we have to distinguish the fact that whilst both of these are called iron chloride, one has a different formula from the other. So what we do is we write it out as iron 2 chloride or iron 3 chloride using the Roman numerals. Now you've probably seen this back in GCSE, and your teacher likely told you that that tells you the charge. This is just clarifying why we use those. So it's just to confirm the different oxidation numbers, because we can have different charges. If we look at KMnO4 and K2MnO4, again we're getting different oxidation numbers for the manganese. It can be 7 or 6. So we have to put that into our systematic name. So potassium manganate 7 or potassium manganate 6. And lastly, the same with the chromate. Here, CrO4 2- and C2O7. In this case, both of them are -6. So both of them would be called the chromate 6 ion, but sometimes you may see this bottom one written as dichromate ion. But it's always important that you put in the brackets with the Roman numerals. So if we look at an example, deducing the formula for iron 2 sulfate, well, this is saying that the iron has a charge of 2+, and we know that the sulfate is SO4 2-, so has a charge of 2-. The two ions would then be present in a 1-to-1 ratio, because we want our overall charge to be 0. So our formula is FeSO4. For iron 3 sulfate, it's slightly different. So the iron in this case has a 3+ charge, and the sulfate has a 2- charge. Again, we want the overall charge to be 0, so we have to multiply these, and we have to multiply the 3+ by 2 to give us 6+, and multiply the 2- by 3 to give us 6-. Now, the overall charge again, is 0. So they are present in a 2 to 3 ratio, giving you the formula Fe2SO4 3. Now, the last part of this topic is looking at full ionic equations. Now, you have met ionic equations before. You've looked at it back in topic 1, and if you did triple at GCSE, you will have also seen that in electrolysis as well as in the reactivity series. What you probably didn't do is combining the two together, and it's actually very, very simple. It is all a case of balance, and we have to balance out all like terms. The one thing that you do not ever want in a full ionic equation is there should never be any electrons. So electrons are the thing that dictate how you balance these. So if we look at here, we've got Fe2 plus giving us Fe3 plus and 2 electrons, with chlorine plus 2 electrons giving us chloride ions. We have got 2 electrons on either side of the arrow. Notice that I want to align all of my arrows so I can be looking at the left-hand side and the right-hand side. It just makes it a little bit easier for you. So because these electrons are balanced already, they are going to cancel each other out. And all we do is we rewrite the equation just by collecting all of the terms on the left and then the arrow and all of the terms on the right. And this is the full ionic equation. And it is made from the half equations. For your half equations, one of them will always be a reduction and one will always be an oxidation, so your electrons will always be on separate sides. If we look at the other one, you can see that we have got 5 electrons and 2 electrons, so these are not balancing out. So what we have to do for the top one is we have to multiply everything by 2, and for the bottom we have to multiply everything by 5. So that would give us 2 MnO4, it would give us 16 hydrogens and 10 electrons, with 2 Mn2 plus and 8 waters. That would then give us 5 H2O2s plus 10 hydrogens, 5 oxygens, and 10 electrons. Now I can balance out my electrons and I remove them, but notice that on both sides there is also hydrogen ions. They must also be removed to balance out. All like terms have to be balanced. So if I have 16 on the left hand side, let's put my line in again. I have 16 on the left hand side and 10 on the right hand side, so that is going to balance out to 6. And then we again just combine everything to give us the full ionic equation. For everything on the right hand side, giving you everything on the left hand side, giving you everything on the right hand side. Now we can also balance equations using oxidation numbers. You've previously been balancing equations simply by looking at the number of atoms or the moles. Sometimes what they will do is they will make it a little bit tougher and they could ask you to look at the oxidation numbers. So the first thing that you should do is identify all the oxidation numbers and look at what has changed. And in this case, you can see that we get a change of sulfur from 4 plus to 6 plus, which is a 2 electron change. So I need 2 electrons for that half equation. The silver is going to have a 1 electron change. Now the problem with this is then those two things are not balanced out. They are in a 1 to 2 ratio. So that means I would need to have multiplied everything with the silver by 2. So that tells me that I have 2 silver ions for every 1 SO2. And again, I'm going to make 1 SO4 for 2 silver ions. And then the last thing you do is simply balance out the hydrogens and the oxygens. And you do that getting this full ionic equation, and you just check that your charges are the same on both sides. and that balances the equation. Now, this does not come up in exams very often, but it can come up. So please be aware of this. And this would likely be maybe a 2 or 3 mark question. If you want to practice, there are lots of questions in the A-level textbook, or of course, ask your teacher. So let's finish off by looking at some past paper questions. These questions will typically be hand in hand with topics 8B or 8C, looking at the reactions of group 1, 2 and 7. So I've only pulled 2 questions here. What you may find when you start to do past papers is the redox questions will incorporate lots of different topics. So for the multiple choice from the January 2019 paper, it is which equation does not represent a disproportionation reaction? So remember, this is the same element being oxidized and reduced. So we should see the same element in 2 species of the products. That's a nice, easy way to determine if you have a disproportionation reaction or not. So you can see all of them is going to have chlorine in it, so it's probably the chlorine that we're looking at. So I have 1 reactant giving me 2 products for A. B, 1 reactant giving me chlorine and 2 products. C, 1 reactant giving me 1 product. And D, 1 reactant giving me 2 products. So the only one that does not give chlorine in 2 separate species is C. And in this question, iodine reacts with sodium thiosulfate solution. State which element is oxidized and which is reduced, giving the relevant changes in oxidation number. So let's work out the oxidation number of everything in this. So iodine is going to be 0 because it is uncombined. The sodium is going to be +1. My oxygen is going to be -2. But of course, if I rewrite this up here, if this is +1, I have 2 of them to give me +2. This is going to be -2, but I have 3 of them giving me -6. So my sulfur should be +4, but I have 2 of them. So I have to divide it by 2 to give me an oxidation number of +2. I then go to my products. My sodium stays as +1. This time my iodine has went to -1. And if I take the Na2S4O6, my sodium has stayed the same at +1, and I have 2 of them. My oxygen is still -2, and this time I have 6 of them, and that gives me -12, which means I must have my sulfur as +10, because the +2 and +10 would give us the -12. So I have to then divide that by 4. Now this is where you might get a bit confused, because in this case, it gives you a decimal. It gives you an answer of 2.5, but that is perfectly acceptable. You would never get anything other than a half, but you can get oxidation numbers of a half. So don't think if you've got a fraction that you've done it wrong. So then we have to say which one is being oxidized and which is being reduced. So the sulfur changes from +2 to +2.5. So because its oxidation number is increasing, it is being oxidized. And the iodine changes from 0 to -1. So its oxidation number is going down, therefore it is reduced. And there you can see the mark scheme for these answers. So we've got C, which we said was correct, and then the sulfur being oxidized and the iodine being reduced. And let's look lastly at the June 2019 paper, which is just, again, determining oxidation numbers. And it is the same examples as we've just looked at, but let's just confirm we had S2O3 2 minus, and we want to calculate the oxidation number of sulfur. So oxygen is always minus 2, and I have 3 of them, which is minus 6. If I want to go from minus 6 to minus 2, I need to have this as a total of plus 4, but because I have 2 atoms, I have to divide it by 2, which gives me a charge or an oxidation number of plus 2, which is A. And for part B, I have S4O6 2 minus. So my oxygen is 2 minus times 6, which is 12 minus. I want to go from 12 minus to 2 minus, because that's my overall charge. Therefore, I need the sulfurs to be plus 10. But I have 4 atoms, so I divide it by 4, and that gives me an answer of plus 2.5, which again is A. So as you can see, we have both answers as A. That's everything for 8A Redox. If you have any questions, please feel free to leave any comments below. My biggest piece of advice for this would be to practice assigning oxidation numbers and balancing using oxidation numbers. And as I said, you can find lots and lots of examples on the internet or in the A-level textbook. We hope to see you back on the channel soon for further revision videos, and if you have any suggestions about other videos, please feel free to leave that in a comment as well.